So how do we account for this non-ideal behavior? The fact that if we add this other salt, it increases the solubility. The way we do this is through a unit isn't quite the right word, but through the concept of activities. So activities are a concept that accounts for non-ideal behavior. And particularly this is relevant for ions. So this does apply not only to ions, it applies to neutral species in solution as well. But the reason ions matters so much is that we have positive and negative charges, and these very strong intermolecular forces lead to non-ideal behavior. So we get attraction between opposite charges, right? So a positive and negative ion will pull on each other, and for two ions that have the same charge, they're both positive, we get very strong repulsion, much stronger than, say, van der Waals forces or something like that. So because of these strong intermolecular forces, we can think of ions, say we have a positive ion here, a negative ion here. We can think of ions as having what we refer to as an ionic atmosphere, meaning their charge influences the area around them. So for a positive charge, it'll attract negative charges to it, and so there is a small negative partial charge kind of around the positive ion. Same thing for a negative ion, we'll have a small positive charge, sort of as an atmosphere, right? Because on average, you will get positive things next to negative things because of that attractive force, and you're pushing away the things that are the same charge, so they will be less likely to be there as well. So these ionic atmospheres affect how ions interact with each other. And we take account of that using this idea of activity. Now, the amount of ions in solution is going to affect how much this matters, and we use a concept called ionic strength to sort of quantify, to quantify how much of an effect this will have. Basically, the more ions you have in solution and the higher their charge, the more this is going to matter. If you have pure water, as we saw, if there are no ions in solution, or very, very few, you're not going to have these effects happening. And so ionic strength has a mathematical definition. We give it the symbol mu. This is the Greek letter mu. And it is defined as 1/2 times the sum of all of the charges, concentrations. C is concentration and Z is the charge. The concentration of each ion in solution times the charge of that ion squared. So just to reiterate what these definitions are, Ci is the concentration, usually in molarity, of ion I, and Zi is the charge of ion I. So let's just do a quick example of a calculation of this, just to show you how this would work. Say we have a solution of 0.010 molar sodium sulfate. Now, when we're doing a calculation involving ionic strength, we have to think about the concentration of each ion individually. So when this salt dissolves, we end up, for the concentration of sodium ions, we get 2 ions per formula unit here. So the concentration of sodium is actually 0.02 molar. We need to remember that in the ionic strength formula. And the concentration of sulfate will just be 0.010 molar because we just get 1 sulfate per formula unit of the salt. So then we can go ahead and plug this into our formula here. Mu is equal to 1/2 times our concentration of sodium is 0.020 molar times +1 squared, because our charge on our sodium is +1. And then we'll have 0.010 molar times -2 squared. And we can plug that in, and we'll get that mu is equal to 0.030 molar. So the effective concentration of ions in solution, because of the -2 charge, so kind of two things happening here. We have 2 moles of sodium for every mole of sodium sulfate that dissolves, and we end up with that -2 charge matters more on the sulfate than the +1 charge on the sodium ion matters. So that's just one example of how we can do this calculation.